In today's video, what we're going to do is tie up a couple of loose ends that we have from talking about the phase behavior of two-component mixtures. And I mentioned this in office hours. We're not going to talk about it this semester, but you can quickly complicate things by moving to even more components. So you can take a similar approach to what we've done so far and go to three-component systems and higher, and the phase diagrams just get that much more complicated as we do that. So a couple things. The first thing I want to talk about is scattering, because scattering is one method that allows us to take all of this nice theory that's been developed, so the Flory-Huggins theory in particular, and connect it with some kind of physical thing that we can measure. So on one hand, yeah, we can connect our Flory-Huggins theory to experiment by doing things like looking at the phase diagram of our system with respect to temperature. And of course, that's very commonly done. So if we have an Lcst system like this, then what we can do is we can go and measure the different characteristics. So we could measure this binodal curve very easily. One way that you might measure this binodal curve is what you'll find is that when things start phase separating, you're going to form droplets in this region, right? So if this is the critical volume fraction, and let's just say for simplicity that it's about 50%, then experimentally, if I move to this side of the phase diagram or this side of the phase diagram in terms of composition, then what my system will look like is, because the two components are not equally mixed, in other words, there's more or less of A than there is of B, then what I tend to get is a bunch of droplets that are within my system. And these droplets will be embedded in a matrix of the majority component. And so I kind of described this to you when we talked about nucleation and growth. So here is the majority phase, whatever that is. And what happens is, if you go back to what happens with light scattering, eventually these droplets are going to get big. These droplets can be hundreds of nanometers eventually. And when you start getting to that size, and you start to approach the wavelength of visible light. So what that means is that if you have something that's very nicely dissolved, let's say you put it in a cuvette in the lab. So I have something like this, and I fill it up with my polymer solution, then if it mixes, it'll be completely transparent and light will go right through like this. So if you were to measure the transmission of light, when you look at the other side, would be 100%. Now, what happens when these droplets start to get bigger is that they start to scatter light, because they become close to or on the order of the wavelength of light in terms of their size. So let's just say this is if you have mixing. And so the reverse is true. If you had demixing of your components, then you will start to get scattering from droplets of your minority phase. And this is, again, because of a difference in the index of refraction and because of their size. Then what you'll start seeing is that this solution becomes translucent. So if you were to, again, measure the transmission of light on the other side, through here, you'd find your transmission would approach zero at some point, of course, depending on how bright your laser is, but you're not going to see anything. So the way that you would explore this diagram experimentally, and if you're ever interested, you can do this in my lab, is you would do what's called a cloud point measurement. And so you would measure the transmission of light as a function, let's put transmission, as a function of temperature. And what you would find for an Lcst system is that, let's label this, let's say this is 100% transmission. And obviously this would be 0% transmission. So if you were to measure this in the lab, then you would find that you get really nice transmission of light. Your solution is clear. And eventually when you get to the Lcst, you start to form those droplets those droplets of the minority phase embedded in the matrix of the majority phase. So you're going to get scattering, and your transmission will then drop down to 0. So this point right here would be your LCST. So you could do this for a variety of volume fractions, and you could trace out the binodal curve, the curve that I'm showing in red. You could trace it out this way. So that's fine. What you tend to measure, in fact, what you measure at this point, is always going to be the binodal line. So this kind of measurement would be called turbidimetry, turbid, because the solution becomes turbid. Metry, because we're measuring it. These are also called cloud point measurements, because you're looking at when the solution becomes cloudy. So at what point does your solution become cloudy? So what you always measure in this case, no matter if you start here in the spinodal region, or whether you start here in the binodal region, remember, when you phase separate, the compositions of the phases that you get will be the compositions of those stable points. So these are the binodal points that you can get from the free energy. So these are the phases that you always form. So what the light scattering, or I guess I should say the cloud point measurements, are telling you in this case, the cloud point measurements are mapping out the binodal. Okay, so how might we measure the spinodal line? Well, the spinodal line is well described by the Flory-Huggins equation. So we know how to find those points because that's just where the second derivative is equal to 0. In other words, where the curvature changes. So how might we do that? Well, the answer, as it tends to be with many phenomena in polymers, is that we would look at some kind of scattering measurement. And the best way to do this is to do neutron scattering for a couple of reasons. One is that you get good contrast between the two components. So you can deuterate one and leave the other one hydrogenated. The other reason is that it's very easy to put neutron scattering measurements on an absolute scale. In other words, when I measure something with neutron scattering, it's much easier if I plot my intensity as a function of Q. It's much easier to plot the intensity such that it has units of inverse centimeters. So this allows you to really access the thermodynamics of your system. On the other hand, if you were to do X-ray scattering measurements, it can be a little bit more complicated. It's possible, but it's a little bit more complicated to put your intensities on an absolute scale. So if you were to look in the literature at X-ray scattering measurements, you'll typically see intensity as a function of Q, and then you'll see that this is in arbitrary units. Or they'll put AU or something like that. So the data will look the same, but you don't know what the absolute value is on the y-axis. You don't know what the absolute numerical value of the scattering is. So that's why you typically do neutron scattering measurements. So comparing these cases, again, if cloud point measurements are giving you the binodal curve, how would you get the spinodal curve? Well, there's a problem on the homework that you're going to do where you would derive what those points are, what the spinodal curve is. So if you know the chi parameter, then you can derive the spinodal curve, right? Because you take the derivative or you take the second derivative, set it equal to 0 and see what happens. So you need the chi parameter for that. So the first thing I want to talk about today is how we might analyze this to get the spinodal curve experimentally. And the way to do that is to remember that in general, when we do a scattering measurement, we're going to focus in on some part of our sample. And so this region that we're looking at will have a size that's basically equal to 1 over Q. And inside this region, we're going to have monomers. And there's going to be a certain number of monomers as a function of Q. So as I make Q bigger and bigger, I'm going to see more and more of the molecule, right? Because I'm going to, as I make Q smaller, As I make Q smaller, I'm going to larger and larger length scales, so I'm seeing more of the polymer chain. So inside this region, we did the same thing when we talked about analyzing small angle neutron scattering. There's going to be a certain number of monomers in here. Actually, there'll be a certain number of monomers on average. And eventually, when Q gets really, really small, we see the entire size of the molecule, and N of Q is going to saturate at the number of A monomers per chain, at least if it's in a dilute solution. So what we need to do then is to figure out how these composition fluctuations that are happening in our system, how those are related to the free energy of mixing, and how we might see this with a scattering measurement. So let's say that there is a fluctuation. So I have a certain number of monomers in this region, but that number of monomers is not fixed. So let's say that there's a certain volume fraction on average of A monomers in my system. So I can always have a composition fluctuation, and the size of that fluctuation will be the local volume fraction minus the average volume fraction throughout the system. So I can also multiply through by n. So if I multiply by n the total number of particles in my system, then n times d phi would be n times phi minus phi bar. And remember, this is the average volume fraction of A. And this is the local volume fraction of A. So if I multiply the volume fraction by the number of particles, what I will pull out is this will become the fluctuation in the number of A particles. And if I multiply through by n, I'm going to get the number of A particles minus the number of A particles on average throughout the system. So the question is then, if I have this, what does this do to the free energy in my system? Well, let's first look at this little region. So what is the change in the free energy when this happens? Well, let's just look at the free energy of mixing. So if I redraw this to be very clear about what I mean, inside this region, I'm going to have a fluctuation in the number of A particles. Let's say that I gain a certain number of A particles. So what's going to happen is I'm going to gain Na particles. And remember, this region that I'm drawing in yellow is what the scattering measurement is seeing. So this is the scattering measurement seeing a size R, which is equal to 1 over Q. And so in that region, I'm going to gain a certain number of A particles. And that means that I lose out here, I'm going to lose A particles. In fact, I'm going to lose Na of those particles. Cool, all right? So my local region has gained a certain number of monomers, certain number of particles, and the other region of the system has lost that number of particles. So the first thing that I want to do is I want to look inside this region. This means that the volume fraction out here is basically phi bar, and the volume fraction of A in here will be phi. And you're going to say, well, wait, if the average volume fraction is phi bar, and I get an enrichment of A in this region so that I have what I call phi now, shouldn't the volume fraction out there go down? The answer is yes, it should, but the rest of the system is so big that that loss of a small number of A particles doesn't really affect it that much. So what I'm going to have is in here, I'm going to have a new value for my free energy of mixing. So delta F of mixing, and notice there's no bar on top. So this is not per lattice site. This is the extensive value of the free energy of mixing. It will be equal to the free energy of mixing at whatever volume fraction that is, phi. And then out here, the free energy will be roughly that of phi bar, but not quite. We're going to account for the loss of the particles in a second. But more or less, it's just equal to what it was to begin with, because it's so much bigger than this region where I've gained a few particles. So there's a meme going around on Twitter right now, and it's basically the difference between mathematics and engineering and physics, but it has to do with Taylor series expansions. So the question is, what does this fluctuation in phi do to my free energy? We're going to expand the free energy. So in this region, I'm going to get a new value for the free energy. So delta F of mixing at this volume fraction is basically going to be delta F of mixing at that average volume fraction plus a perturbation due to the fact that I've gained a certain volume fraction of particles due to the fact that there's been this fluctuation. So if I expand around this point where delta F, or expand around the point delta F of phi bar, then I'm going to get, this is equal to plus the partial derivative of delta F of mixing with respect to phi times the size of that fluctuation d phi. That's the first order correction to the free energy. And then plus a higher order term, so plus 1/2 times the second derivative of delta F of mixing times the size of that fluctuation squared, and then plus higher order terms that we're going to ignore. Okay? All right, so if you look at it, this is the average free energy of the system. This is how the free energy changes by gaining or losing a certain number of particles, or how much the free energy increases or decreases because of this fluctuation d phi. Now what I can do, let's just look at that one term. Let's just look at the first order term. And if I do that, this term looks like the derivative of delta F of mixing with respect to phi times the size of that fluctuation. That's the first order term. And let me multiply through by the total number of particles, so n by n. So this would be n by n multiplied by the derivative of delta F of mixing with respect to phi times delta phi. Well, what I can do is I could take this n and bring it on through, and I could take this n and bring it on through. N times phi, remember phi is the volume fraction of A, that is equal to Na, the number of A particles. So this will be equal to delta, or the derivative of delta F mix with respect to Na times the fluctuation in A particles. So this is like a chemical potential, right? It's how much the free energy is increasing or decreasing when I add or remove Na particles. So we call this term an exchange chemical potential. It's how much the free energy increases or decreases when I swap one A particle for a B particle. So let's put it in words. How much delta F of mixing changes by swapping an A particle for a B particle. So that will be useful because we're going to have to incorporate this into our expression for the free energy. So let's go back to the problem, which is this drawing right here. That region that I've circled in yellow is going to gain Na particles, and the bulk system will lose Na particles. All right? Now, why does this happen? Because of a composition fluctuation. Why was there a composition fluctuation? Because there's thermal energy. Things are moving around. So in other words, what's happening to my entire system? So the system that has the little region that I've circled and then the bulk system is there's going to be a tiny change in the free energy of my system. And that's due to the thermal fluctuations or due to the composition fluctuations that were caused by the thermal energy. So that means that the magnitude of this change in the free energy will be about kBt. And that's going to equal what? Well, it's going to be the free energy of mixing of my region that has the volume fraction of phi. So this is that little tiny region that gains a certain number of A particles. And then it will be minus the free energy of the rest of the system, which has an average volume fraction of phi bar. But then look what happens. If we have this exchange chemical potential, this is how much the free energy changes if I lose or gain Na particles. So that means that I also have to subtract the free energy, or subtract from the size of this fluctuation in free energy, the amount that the free energy has changed in the other part of the system. So minus the derivative of delta F mixing with respect to Na multiplied by the number of particles that I lost. So then this whole thing here is what happens in the rest of the system. Now I already have an expression for delta F of mixing. I did the series expansion, right? So that's equal to this term here. So I can substitute it in, and you'll see that a lot of terms will cancel. In fact, let's just do it to be complete. We've got delta F mixing phi bar, and then plus the derivative of delta F mixing with respect to Na delta Na. So there's my exchange chemical potential. Then plus 1/2. Let's just leave this term in terms of phi. So delta squared delta F mixing over d phi squared delta phi squared. So all of that comes from that first term. I just expanded it in terms of how we defined it from the series expansion that we did. And then we'll have to subtract off the rest. So subtract off the orange stuff here. All right. So if we do that, we have minus delta F mix phi bar minus the derivative of delta F mix dNA. So a bunch of things are going to cancel in this case. We get that cancels with that cancels with that. And all we're going to be left with is that little fluctuation, or that term there, which describes the fluctuation in the free energy. So in other words, the fluctuation in my free energy has a magnitude that's about kBt, which is equal to 1/2 delta squared delta F mix for d phi squared, and then multiplied by the size of that fluctuation squared. Is that useful or not? Well, the answer is yes, because why would we do it? So let's think about what happens. When I do a scattering experiment, if I go to low enough Q, eventually I see the entire molecule. In other words, the number of particles saturates. When I see the entire A particle, the number of monomers saturates because I'm seeing everything that's possible in that molecule. So that means that, if you remember our definition, if the structure factor term is defined as the number of monomers in that region divided by n, then this would be equal to, well, I could multiply through by n squared, so I could have n squared let's see. Or this would be the same thing as delta phi q squared divided by n. Okay, so I factored out the n to get the volume fraction. Okay, so this is the volume fraction in a region that has a size 1 over q, and then we've got the n term. So this is equal to size of the fluctuation in that region, q squared divided by n. Now again, let's look at what happens. As q gets smaller and smaller and smaller, we get to larger and larger regions, and eventually we see everything. We see all of the monomers in that A polymer. So if we do that, then S, as q goes to 0, should be equal to, well, it's going to saturate at the size of the, it's going to saturate at a fixed value, which is Na, the total number of particles in that region, the total number of particles that make up the chain. So this is going to be also then delta Na squared divided by n, which will be the same thing as delta phi squared divided by n. Oh, wait, what did we just do? We could measure the scattering. We could measure the scattering from a solution. And now I've just showed you that the scattering that we see is directly related to the size of the fluctuations in the volume fraction of A. But we kind of have an expression for that, right? Because let's just leave off this 1/2. Who cares about these little prefactors, really? So in that case, we can see that the size of this fluctuation squared, on average, of course, is going to be kBt times the second derivative of delta F mix with respect to the volume fraction of A to the -1 power, just rearranging that expression for delta F. Well, sweet. We have everything. So the structure factor at very, very, very large length scales is going to be equal to kBt times the second derivative of delta F with respect to phi squared. Of course, these are both, well, this would be divided by n. And delta F mix divided by n is just delta F mix with a bar on top, right? It's per lattice site per particle. So this is the same thing as kBt delta squared delta F mix phi squared to the -1. Well, that's really convenient, right? We've got something we can measure experimentally and a derivative of the Flory-Huggins equation, which we know. So this means I can also write this as 1 over S0 is going to be the second derivative of delta F mix with respect to phi squared, and then this becomes 1 over kBt. Well, we've taken the derivative and we've taken the second derivative of delta F mixing. So this will be equal to kBt, and then we've got the 1 over kBt from that. So obviously those will cancel. So let's not even bother writing them. And then what do we have left? Well, we've got 1 over Na times phi plus 1 over NB times 1 minus phi minus 2 times chi. And that's 1 over S0. So now we can measure the spinodal curve. Because what we'll do is we'll measure this at multiple values of temperature where the system dissolves, so in the one phase region. And then we'll fit the expression to find that. So now we've got chi as a function of temperature. And so if we have chi as a function of temperature, well, we can take the second derivative and set it equal to 0 and plug that value of chi in and map out what the spinodal temperature is at all of the different volume fractions and things. So we can extrapolate from the values of chi that we've measured to get the spinodal line. So once we fit to find chi, then we can write chi as a plus b divided by t, and we can extrapolate to figure out what the spinodal line is. So that's it. That's how we do it. We've got the binodal line from cloud point measurements if we want, at least in the case of polymer solutions. We can do these measurements both on polymer solutions and polymer blends in the one phase region to get chi. We can fit to get chi from the measurements. Then we can calculate the spinodal curve. And actually, we could calculate from this. We could calculate the binodal curve and the spinodal curve. That's pretty cool. So this approach is useful, but notice that it's at Q equals 0. In other words, it's looking right down at the incident radiation. And again, like I've discussed, for a variety of reasons, we cannot measure S of Q equals 0. We can measure close to it, but we can't measure exactly that. So you can take an approach, and we won't do it here. It's much beyond the scope of this class, but we can take what's called the random phase approximation. And if we do that, then what we get for our expression is we get an expression S of Q. So we get the structure factor at all values of Q, in other words, all length scales. And this looks very similar to the expression that I just wrote, except now we have to take into account the angular dependence of the scattering. And so we will get that this is equal to 1 over NA times phi times the form factor of the A chains, and you know what that is now, and then plus 1 over NB times the volume fraction of B times the form factor of B. And if B is a solvent, then the form factor is equal to 1, always, minus 2 times the Flory-Huggins parameter, which is a function of temperature, to the minus 1 power. And so this is super, super, super important. This is how we know so much, or one way that we know so much about polymer thermodynamics. And so what you'll find when you measure things is because this depends on chi, and maybe it's easier to see here, it depends on chi, and so therefore it depends on temperature, then basically the interactions are going to modify our scattering graphs. So what we'll find is that before we even fit anything, if we plot I of Q as a function of Q, then we could see curves that look like this. So the polymer chain, when it scatters, looks like this. And we might find, I'm exaggerating it slightly, but we might find that the intensity increases. So we might find that I of 0, which is these points, we might find that that increases as T increases. That means that the composition fluctuations are getting stronger as temperature increases. So this is a signature of an LCST system. And you have to be careful. This is why you take interactions into account, because remember, the y-intercept, we always said, tells us something about the size of a molecule. That's certainly true. But if you have interactions in your system also, then you can see that it increases your intensity. So it's not just due to the size of the molecule, it's also due to interactions and composition fluctuations. So if you didn't use the RPA, you might think that your chain is getting bigger as you increase the temperature. But we know that for LCST systems, the interactions are getting less favorable. So in that case, the chain should be collapsing. And if you use the RPA, you will find that indeed your chain is collapsing and interactions are getting less favorable. The reverse is true. So if I have a system like this, I plot intensity as a function of Q, I may find that my intensity decreases. So it may be the case that the intensity decreases as T increases. This is going to be a sign that interactions are getting more favorable. And so the intensity is decreasing. This doesn't mean that your chain size is getting smaller. It means that interactions are becoming more favorable and your composition fluctuations are going down. So this is a signature of a UCST system. Okay, so that makes it sound kind of easy. These measurements are, they can be a little bit more complicated. And what you would do is, in general, we've expressed chi in this very simple way as A plus B over T. That doesn't always cover it. Sometimes you need to include terms that depend on the volume fraction. And so I assigned a homework problem where you will do that. Other times it depends, the chi parameter depends on temperature in a little bit more complicated way. So 1 over T doesn't quite describe everything. And you can include a second term, either C over T squared in some instances, or C times the logarithm of T, and potentially other interactions, other terms. And so that inclusion will lead to a richer set of phase diagrams than just UCST or LCST systems. So let me give you some examples. Your phase diagram, remember, in terms of chi, always looks one way. But in terms of temperature, it can take on a variety of shapes because it includes how the chi parameter is changing with respect to temperature. So, of course, you could have your standard UCST system like this. So, of course, this is UCST. And this will result when B is equal to, or B is greater than 0, and C is equal to 0. An example of this would be deuterated polybutadiene and hydrogenated polybutadiene. Remember, when you mix hydrogen and deuterium together, when you get to high molecular weights, those two polymers will not like each other because of the heavier isotope. Kind of a cool effect. And if you do a lot of scattering, sometimes it's something that you need to worry about. So that's obviously UCST behavior. We saw that we can also have LCST behavior, where the graph would look something like this. And to get LCST behavior, basically you would have a B that's less than 0, and C would be equal to 0. Okay, so the two cases that we've seen so far have C equal to 0. In other words, we don't include that logarithmic term with the temperature. There are other ones though, so we could have a closed loop kind of diagram. So we could have something where the binodal curve is circular and the spinodal curve is inside of that. So to get this type of shape, you would have B less than 0 and C less than 0. And an example of this would be polymethyl methacrylate plus polycarbonate. So it has a little bit more complicated phase diagram. And obviously everything out here is where the system mixes. So at intermediate temperatures and intermediate compositions, the system will not mix, but outside of those two regions, there's no miscibility gap and everything dissolves quite well. That's not all though. You can have yet others. So you could have something that looks like this, where your binodal curves look almost hyperbolic. And you have your spinodal curves like that. And in something like this, you would have B greater than 0, C greater than 0. And an example of this would be high molecular weight polystyrene and acetone. Okay? So high molecular weight polystyrene will mix out here, but at intermediate volume fractions, it will not mix, and it will decay, it will phase separate by either spinodal decomposition or nucleation and growth. And then the last example, same conditions, but different shape. So it's going to depend on the other coefficients relative to each other. But you could have a phase diagram that looks like it has UCST and LCST behavior. Oops. Like this. And so in this case, still B is greater than 0 and C is greater than 0. But look how or look at the shape of this phase diagram. An example for this phase diagram would be not high molecular weight, but low molecular weight polystyrene and acetone. So you can see the effect of the other variables. So in this case, the degree of polymerization of the polystyrene chain on the phase diagram. And then in this region, you would get mixing. And then in the other regions, you would get either spinodal decomposition or nucleation and growth. So that's just touching on a few things that happen in these systems. There's much more to be said. So we've talked about dilute solutions, and we've talked about polymer blends. We haven't talked about the intermediate cases, so things that we have not talked about. We have not discussed semi-dilute systems, where you have some regions where the solvent plays a big role, and then other regions there's so much polymer that the solvent doesn't play a role. So it's kind of a combination of the two. If you study polymers further beyond this class, this is a condition that happens a fair amount, and so it's something that you're going to have to take into account. We have not talked specifically about the Flory-Krigbaum approach, but we will come back to it when we talk about Flory-Rayner theory. So we'll talk about this dilute solution case when we talk about the swelling of polymer gels and networks. So we'll come back to that. And the other thing that we haven't talked about too much is strategies to mix these immiscible phases. So very briefly, I want to talk about one of those things that you could do. And so the first one is block copolymers. And in the simplest case, what this entails is you have one block that's A, one block that's B, and these are covalently bound to each other. So you have A and B, and because they're linked at that junction, they can't fully phase separate from each other. So in this case, depending on the fraction of A, let's say the fraction of A in the chain, if you make a melt out of these, then you can get a wide variety of morphologies. So if you have, well, in one case, what you could get is, let's say that FA was on the order of like 25%. Then what you would see in your TEM images is a bunch of spheres. And they would be embedded in a matrix of the majority polymer. So this would be something like polystyrene block, polymethyl methacrylate. You could start increasing the amount of the A polymer that you have. And so you could have something like FA is like 35%. And then in this case, maybe I should draw this in 3 dimensions, actually. Let me do that. Let's draw this in 3D. You're going to change the morphology of the A because now there's more A in the system. So in this case, you would have cylinders that form, and the cylinders are packed hexagonally. So here you have a body-centered lattice with body-centered cubic lattice with spheres. Over here, you would have a hexagonal lattice of cylinders. There are other phases that you can form. So eventually, when you get to about 50% A and 50% B, you'll form these lamellar structures. So this would be lamellar. And this would occur when like the volume fraction of A is close to 50%. And it's worth pointing out the length scale that I'm talking about here is like 100 nanometers or maybe less. So while it looks like it's phase separated, it's not fully phase separated where you have micron scale domain sizes. So block copolymers allow you to better blend these. And then as you increase the fraction of A further, you just go back this way and invert the structure. So a lot of work has been done on this over the past couple decades to map out the phase diagram. And the phase diagram roughly looks something like this. I'm not doing it total justice here, but you have a point here. Called the ODT. It's the temperature at which you transition from being an ordered structure. So up here is an ordered structure. And down here is a disordered structure. So it's like a critical point beyond which you start phase separating. And then your phase diagram, you've got spheres, cylinders, lamellae. Sometimes they write this as hex. Okay. So this has been mapped out in great detail. I'm not talking about everything that there is to talk about this. This is a really rich field. But you can look at the work of Frank Bates, as well as Mark Madsen, who did theory and experiments to really map out and understand this phase diagram. And you can even go beyond this. This is for a diblock copolymer. But you can go even further and tri-blocks, tetra-blocks, all kinds of things. Okay, so that's one strategy to get the two to blend together. Another one is that you can use a system where you've got A and B in die blocks. So in this case, the die blocks act as a surfactant. And what you end up with is a microphase separated structure, where let's just say you've got regions like this. So the length scales that we're talking about here are handwriting, they're submicron. And the reason that they blend is that you have these chains at the interface that are covalently bound to each other. And so these help emulsify the two components. It's similar to making salad dressing. You mix oil and vinegar together and you'll see that they quickly phase separate. What do? If you want to make a vinaigrette, you add a tiny bit of mustard. The mustard has lecithin in it, which acts as an emulsifier and helps blend the two components together. Same thing with oil and water. If you put soap in, soap will help emulsify the oil and water phases by acting as a surfactant. In other words, acting as a surface active agent or surfactant. The last example that I showed you is you can use nanoparticles. And I showed you two examples in the movies of rod-like particles jamming one of the phases, or particles that go to the interface and jamming the structure. And in that case, the particles that go to the interface, something like this with these small phases. And then you get these big particles at the interface. These act like surfactants. So it's the same kind of idea, except instead of using die blocks, you're using nanoparticles to keep the two phases together, because these particles become jammed. Woo! That is too big. I thought I'd try it. I failed. They become jammed at the interface. I'm sure there's myriad other ways that you can blend these together. It was a really hot area of research in the mid-90s, early 2000s, and some people are still working on it today, but you have to start playing tricks to get these two things to blend together. And so with that, I'm going to just conclude by saying I haven't covered everything. I've covered the key details, the foundations through which you can understand mixing two or more components together. But the subject is very rich. There's all kinds of things that you can explore in addition to this. And with that, that's it for today. And we'll start up in the next couple of videos on a brand new topic.